All right, I think it's a good time to start. Good morning, good afternoon, good evening. Welcome to the Topology Optimization webinar. It's my great pleasure to welcome you on behalf of the organizers. To those of you who might be joining Topology Optimization webinar for the first time, the Topology Optimization webinar was, we started 2 years ago at the beginning of the pandemic, with the intention to make it a platform for exchanging knowledge. And we run 20 sessions so far. In April this year, we did a survey, and the reply is very positive, and we got great feedback and suggestions. So this is the first one after in this new series. So we are very happy Shelly Zhang organized this session on topology optimization of architectural material and multi-scale structures. So thank you, Shelly, and please take it over.
Thank you, Jun, for the very nice introduction of the top webinar, and thank you for the thank all the organizers of top webinar to invite me to host this session. So let me first share the screen. I will. Can you see my screen well? Okay, perfect. All right. Hello, everyone. Welcome to, I would say, the first session in the new phase of top webinar. I am Shelly Zhang. I'm an assistant professor from both civil and environmental engineering and mechanical science and engineering from University of Illinois at Urbana-Champaign. So it is my great honor and pleasure to host this session. So today we have this thematic session, as Jun just mentioned. I would like to first give a very brief motivation, the introduction of the topic that we focus on today. So architected materials and multi-scale structures are quite desirable because of their various superior properties, such as lightweight, high stiffness to density ratio, resilience, just to name a few. And designing this type of multi-scale systems are quite challenging because we need to consider both the microscopic feature as well as the macroscopic features. And topology optimization, as we all know, is a very promising approach to design this type of systems because of its ultimate design freedom. So also the advances in additive manufacturing recently, and advanced manufacturing also made this possible by realizing these optimized designs with complex geometry in order to validate them. So I did a very quick search yesterday on the, let me see, using the keyword topology optimization and multi-scale or architected materials. And here's what I found. And you can see that there is a growing interest over the years, and especially in recent 2 years in this field. So the goal of this webinar is to assemble a group of researchers to present the state-of-the-art development in this area, as well as discuss some challenges and opportunities in this direction. And just want to very briefly mention this type of designing architected materials and multi-scale structures can be characterized into two approaches, multi-scale type of approach, as well as full-scale approaches. And the only difference is that in the multi-scale approach, we are distributing the homogenized materials or unit cells with the assumption of separation of length scale. Whereas the full-scale approaches directly optimize the distribution of the homogeneous material without assumption of separation of length scale. So this webinar will focus on the recent development in using the multi-scale approaches. And for those of you who are interested in this topic, I recommend this following article for a very comprehensive introduction and review on multi-scale topology optimization approaches. All right, finally, just wanted to throw a bunch of initial thoughts to hopefully guide some discussions and questions in this webinar. And hopefully it can be a forum to discuss the opportunities and challenges when designing architected materials and multi-scale structures. So in terms of challenges, For manufacturability, for example, how do we ensure manufacturing ability of the optimized design, especially for 3D multi-scale structures, including connectivity between neighboring unit cells, minimum length scale, or feature size for fabrication, and various requirements from manufacturing side. As well as also in terms of simulation, the main question is how do we get a good balance between efficiency and accuracy? For example, how do we make sure simulation results from the homogenized properties are accurate enough compared to the full-scale simulation? And finally, some challenging problems in multi-scale approaches, problems including buckling, material and geometric nonlinearity, strength, contact. And these challenges also pose as opportunities in the future directions. And I just want to point out that the 5 talks we gathered today represent some of the state-of-the-art approaches to actively addressing these challenges. Without further ado, let me show the final the schedule for today. I'd like to remind you to type questions in the chat window and address the speaker that you are trying to ask a question. So let me introduce the first speaker, and where you can set up the screen on the same time.
Okay.
Yeah. Our first speaker is Professor Wei Chen, and she is the Wilson Cook Chair Professor in Engineering Design at Northwestern University in the US, and the Department Chair of Mechanical Engineering. Wei, you have the floor.
Thank you very much, Sherry, and thank you so much for putting this nice webinar together on this topic that's very challenging, but it's also very interesting. So I'm going to share with you a recent work that we have been doing. It's a very different approach, I would say, because I think a couple of years ago when Jia Dongdeng was my PhD, we worked on multi-scale TO. So everything is under the topology optimization framework. But in recent years, we tested a different method we call data-driven multi-scale design approach. So I'm going to share this approach with you. And this is a joint work among multiple students and also PI here. Kara Durrell is a faculty at Caltech, and I'm at Northwestern. And Liwei Wang, first author of this work, he's actually here today to help answer questions you have. He knows the work best. He was a pre-doctoral visiting student at Northwestern when he worked on this project. He was at Shanghai Jiao Tong University, received his PhD there, and now he is a postdoc in my group. And Jake is a student of Kira, and Ke Liu, also called Chris Liu, is now a faculty, was at Caltech postdoc, and now a faculty at Beijing University. So it's really a joint work among a group of people. So the method is more about data-driven and multi-scale optimization, but we're using the string cloaking as example to demonstrate the benefits of this method. So you may have heard about many different kinds of cloaking. An optical cloaking basically makes object invisible, like this Harry Potter's invisible clock that I'm showing here. But in this work, we're actually focusing on what we call the string cloaking. And it turns out to be a much more difficult problem than an optical cloaking. So imagine that you have a structure here that is composed of a homogeneous lattice, and when you compress it, and the displacement will have a linear transformation. You can see here the displacement field. And now if we impose a void in the middle, like if we want to hide objects in the middle in the void, this will introduce a very large distortion of the displacement field. So the question here is, can we design the surrounding area of this void in a smart way that can really making sure that the displacement in the surrounding area is very similar to before you're hiding a void. So this is the so-called string cloaking. And the practical application of this kind of method can be used to protect, say, underground tunnel from stress or string concentration. And this is a soft robot that has some wires, kind of hide in the middle, in the void area. So so most of the cloaking design, like in electromagnetic or thermal fields, they're based on this method called the material parameter transformation. And this method is try to exploit this called the form invariant kind of a condition. But in our case, in the continuing mechanics, we don't really have this form invariant behavior. So this method is not applicable here. And that's really the challenging part. And if you look at the string cloaking design in the literature, most of the methods are confined to special lattice material or some simple shapes of voids. So I'm showing you here some example that's published in the literature. So our idea here, this is actually the idea behind the data-driven, we call the data-driven architecture design, is actually try to consider material as basic building blocks. And now without changing the constituents, the question here is how can we assemble them in the ways so that we can accomplish a very heterogeneous material system? And we all know that the heterogeneity actually is a better way to optimize the performance, because if we use the same unit cell everywhere, which we call the periodic, right? In most of the system we see, that's not the optimal way. The optimal way is try to use aperiodic structure so that it can fully utilize the resource and achieve the best performance. But it really introduced a lot more difficulty in design, in topology optimization in particular. So our approach here, the approach I'm going to show you today for the cloaking problem is called the top-down approach. And we actually have, we call the bottom-up method in several other papers that we published. But this top-down approach here, the idea here is that we're going to create a freeform database, could the unit cell can have any architecture, but we're going to start with using optimization. So it's still a topology optimization framework applied at the top level. But instead of optimizing the architecture, we're going to optimize the property at each unit cell. And then we can retrieve the different unit cell in the library and making sure that they're compatible. So they will have assemble the structure at the end, achieve the performance you want. So that's very different from the bottom-up method. You start with building the constituent relation and feed it to the top level, topology optimization. And in terms of the database, our lab has been doing a lot of work on how we intelligently create this database. I'm showing you just one example here. This is the case that we actually create a unit cell database by using topology optimization, basically specify different targets for the stiffness tensor elements, and then try to identify design. And once we identify those envelope, we do random perturbation. So it's a stochastic method that we try to go beyond the envelope and find a better design. So that's the library that we create. And so for this problem, the top-down approach here starts with a concurrent topology and the property optimization. So I'm using just some illustration here to show you, for example, if we want to hide the object in two voids here, or one void, basically we have two sets of variable. One that represents topology design. This is the traditional topology optimization representation, so 0 or 1 or in between. And then another set of variable is the property value. So in our case, this project is the stiffness matrix. And then combining the two, we form a function here represents the design variable in concurrent design. So for this particular example, you can imagine that we're hiding some voids in this butterfly shape. And the first step is identify the optimum property at each location. So if we're doing this orthopic kind of structure, it will be C11, C12, C22, C33. So identify the optimum targets for each one. And then we retrieve the library to form a compatible structure. So when we retrieve the library, you can imagine that for each optimized property, there may be some multiple unit cell that can meet the property, right? And they're very close, maybe slightly different. So each of them could have bunch, in our case, maybe 10 candidates will be considered. So the question now is, how do we make sure that they're compatible with each other? And the compatibility is defined from multiple aspects. So this is the mismatch example. So how we make sure they're compatible. So we actually model this as a more like a network, and each node here represents a unit cell design. And we have this function related to the energy. So we're minimizing the nodal energy for each node. And this is defined as nodal energy, edge energy, that have two aspects. One is the geometrical compatibility. Another one is the mechanics compatibility. So this function working together, and we have a due decomposition method, a very efficient energy minimization problem, to solve this problem very quickly to put a structure together. So I need to watch my time here a little bit. I will show you a couple examples. Like this first example is a circular void. That's what we predefine. So each unit cell looks like this kind of structure, okay? And we have the load applying from the two sides, and we kind of predefined that there's a void here, and the shape of the cloak region is also predefined as a circular. So that just means that inside it will be, there's a 1 and a 0 is pre-assigned. And once we use our top-down method as well as assembly, and you can see this is the structure, and the objective here is to minimize the difference between the displacement field in the surrounding area with the one that without any voids. So that's objective. That's based on the original cloaking definition. So if you look at here, this is the reference structure in the displacement field, and this is the voided structure without cloaking. And you can see there's a distortion there, the displacement field. And after you add this cloaking layer, you can see the displacement field now is very close to the reference structure. And working with our colleagues in Cartech, we actually fabricated this structure and then also performed the experiments and using the global DIC method to capture the displacement field. So you can see that this is the experiment result. And you can see with the cloaking method, the displacement field is much closer to the original reference, and the one without, you can see there's a big distortion there. So the experiments supports our conclusion very well. We also applied the different various boundary condition, like displacement-free, pressure-free, and many other examples that you can see here. And this method is applicable for all these different scenarios. So the animation here basically show you the deformation after the load and how close they are to the reference solution. Again, the last row is with cloaking, and the middle row is without, and top row is the original displacement field. And we can also accommodate different base cells so that we can have circular shape. In this case, it shows you different unit cell. The lattice structure can be different in the surrounding area. And this shows the solution after cloaking. We also try the different accommodating different loads. In this case, we can simultaneously apply load with a different angle, and the voided structure and the cloaked structure. Again, you see that those structures are, we call it aperiodic, because each unit cell, the result can be very different from one location to another. And this also shows that it's a validation to show the optimized solution accomplished the objective. Various voids, we go from ellipse to star to square and to Mickey Mouse shape. And again, that is just a further validation to demonstration to show you that the method is quite versatile. It can, we can even apply adaptive cloaking region, means that we do not pre-specify the shape of the surrounding region, and let the optimization solution to tell us what kind of, whether it should be a part of the cloaking or not part of the cloaking region. So this is the just adaptive cloaking region. You can see that the surrounding shape can be very different. Now this shape is actually kind of conform to the Mickey Mouse shape in the middle. So you can see here, right? This is just predefines a circular shape. This is the solution, and this is not specify any restriction and let the solution tell us. So it's called adaptive. So you can see this shape is somewhat similar to the one that voids in the middle. Some quantitative measures here that shows you about the objective differences basically is the difference, the error, we call error function, the difference between the after cloaking and before cloaking. And you can see that the solution with cloaking are represented in the red color is much, much better compared to if you don't do anything. So those just are different cases, just different test cases that I showed you earlier. Predefined topology and adaptive topology. And one more animation, I think then I will go to the conclusion. So this is the butterfly shape with two voids in the middle. So you can have multiple, any number that you want. So this is my concluding slides. Oh, this is another one, just to show you a very complex voids and what kind of design a unit cell that is identified as the optimal solution for this kind of problem, for this butterfly problem with two voids. We also apply the same approach to some other problems. So one very straightforward original problem we actually tried before we even tried the cloaking design is this desired displacement kind of problem, right? From changing from crying face to smiley face. And here, like any kind of desired displacement, for example, in robot arm, if you want to make sure that there's some local motion with some desired shape, and this could be used for that kind of purpose. On the right, I'm also showing you here very useful application that is done by another student as the lead author, Da-Chong Dai, and publishing Extreme Mechanics is on fracture resistant design. And here we want to accomplish the goal of toughness that is measured by the total surface like integration underneath this curve. So the structure is not only stiff, that's strong, but it's also tough, means it can last very long displacement. So the blue line and the black line here are the reference structure, the periodic structure A and B. You can see that the purple line is the one that we used this structure using the data-driven method that is aperiodic solution. So you can see that it not only it has the highest force here, also has the largest displacement before fracture and the strongest toughness. So this kind of a problem is, I think I'm closing to my end. So just a summary, I want to just show you not only the references of the top-down approach. In many cases, we think bottom-up framework may be more appropriate. And I'm showing you here some recent application that we actually extended this to general de-homogenization approach. So you can take any angle at a different location. 3D example using blending strategy to further mitigate the issues with homogenization. So I will just end here.
Thank you, Wei, for the very impressive talk. So we are a little bit, so I probably will just ask one very quick question from the first, I think from Ole. Do you want to ask a question? Or I can read it. Okay.
Sure, I can ask it. Thank you for the talk, Wei. So I was just curious, you were considering orthotropic microstructures all the time. What if you limit yourself to isotropic ones? Would you perform just as well, or would it degrade the performance?
I don't think it is restricted to isotropic behavior. It can be used to other kind of unit cell design, if that's your question. I think the key here is to have a set of targets that you're able to optimize in the top level, and that you also make sure they're compatible at the end.
Well, it was more, would it degrade performance if you did isotropic? So it would structures, it would? Okay.
Yes, I think so. I think so. You're right. Yeah. And I think we just used the database we had was also tropic. Yeah. But we can extend it to other database.
Thank you, Wei. Thank you very much. And we have 3 more questions. And Wei, if you could.
Yeah, we will. And myself and Li Wei will both answer the questions. Yeah. Okay. Thank you.
Sounds great. Thank you, Wei. All right. So next, let's welcome the second speaker, Professor Xiao. Would you like to share the screen? So Professor Xiao is an associate professor from the State Key Laboratory of Digital Manufacturing Equipment and technology from Huazhong University of Science and Technology in China. You have the floor.
Okay. Dear Professor Zhang, Professor Sigmund, and Professor Wu, and the other audience, thanks for sharing the invitation to give me my chance to make this presentation. Today, I would like to introduce the design of thermal metamaterials by multiscale topology optimization. My presentation will cover the following 4 aspects. Thermal materials are a kind of artificially designed materials or structures. They have present the freeform, some properties, and these properties are not found in nature materials. As viewed in Figure A, the core materials is placed between a heat source and a cold source, and the simulated temperature distribution is shown on this figure, where the temperature distribution is uniform. When the thermal metamaterials are placed in the anode region under the same boundary in Figure A, and we can find that the temperature filled in the outer region of the circle does not change, but in the inner range, the temperature field present cloak constitution and relation. In design thermal metamaterials, there are 3 methods. One is the transformation semiotical method. This method makes the real new space equivalent to the virtual space when thermal materials fill in the transformation region. This we can see the background, and the blue is the design area. And when put the thermal materials in this area, and the background have the same temperature distribution. The second method is the skirting constellation designed the thermal materials. Using this method, solving the thermal conduction equation enable the fabrication of a bilayer cloak like this. This is the yellow one is the conducting shear, and the green one is the insulating shear. And using this method, we can make a fabrication of a bilayer cloak. And this cloak consists of in the insulation shear and outer conduction shear. And the cloak function can be achieved like in this research works. The third method is the topology optimization method. We can use topology optimization to design the structures to make the temperature field and these optimized structures be the same as the target one. And we can, from these 2 pictures, we can see using the TO method, we can design the structures, and the background, in the background, the temperature field and are very close. However, 3 long-standing challenges exist. One is the thermal materials are usually fabricated in experiments by layer structures, and these structures may have a regular shape like the circular structures, and this will limit their shape adaptability. Second, the transformation semiotics method results in electrolytic materials parameters, and these parameters are hard to realize by later materials. Finally, most topology optimization methods require the preset background temperature field in the optimization process, which in turn affect the design efficiency and flexibility. To overcome this challenge, we use the multi-scale topology optimization method to design thermal metamaterials. This is the schematic of the design process. The first step, we can calculate the required thermal conductive sensor according to the desired functions and the shape. These are the formulas in the transformation semantics. Hey, the second step, we grade the design region into small topology function cells called TFCs, and each cell has the calculated thermal conductivity tensor. And the third step, we take the required thermal conductivity tensor at the goal and design the configuration of each TFC by topology optimization. This is the model, and this is the object, and the other is the constraint function. Finally, we assemble all the TFC to realize the targeted thermal functionality. Here, I will introduce some details in design and assemble of TFC into freeform thermal metamaterials. One is to ensure good collection. We fit the 4 colors of each TFC, and these are the initial, optimized, and reprocessed TFC structures. All the TFCs are assembled. Besides, we need to remove the redundant materials. Then we can obtain the thermal material structures, such as the constituents, the and the cloak. Here, we make the numerical verification for the thermal properties of the TFC. Look at this picture, and this is the pure plate with the target thermal conductivity. And this is the temperature field distribution is calculated by Gamoso. And this is the case 1. Case 1, the TFC had 2 materials, and the temperature field is calculated also by Gamoso. From this picture, we made a comparison, and we find that the temperature views in case 1 and 2 are very close. Therefore, the effective thermal conductivity of the designed TFC is very close to the target. Then we design 3 thermal materials: concentrator, rotator, and cloak. Then we evaluate their functionality in order to verify the omnidirectional functionality, and we make a linear uniform heat flow, and in 4 directions. The heat flow across the thermal materials. These are the simulated results. We can find that the thermal materials can remain function at different heat flow. Moreover, we test the function of the thermal metamaterials under the long uniform heat flow, and also they can remain their function. Furthermore, the transient temperature field of 3 thermal materials are given, and from these pictures and we can see that the function also are kept. Finally, we fabricated thermal materials by 3D printing and implement the thermal experiments. This is the schematic of the experiment setup. The experiment results are very close to the simulated one, and their thermal function can be kept under 2 different directions of heat flow. In summary, we proposed multi-scale topology optimization method for design thermal materials. And this method can overcome the three standing challenges of existing method. And this method can design freeform thermal materials and like this and have more complex shapes. The second, this method can solve the problems that design the thermal materials with anisotropic material properties. And this properties is induced by the transformation symmetrical method. And we can use the topology method to achieve these properties. Finally, and this method is the background temperature independent. This means that we can change the background temperature and the thermal function of the structure will keep. And the change of the background temperature and the function will keep. And this is my presentation, and all the details can be found in these three references. And also I grateful acknowledging the contributions of Dr. Wei Chen, Professor Liang Gao, Professor Ren Hu, and Professor Chen Weiqiu to this research work. More details can be found in these three papers. Okay, that's all. Thank you.
Thank you, Mi, for the great talk. So for the interest of time, I was looking at the questions, so probably the audience are trying to type the questions. So for the interest of time, is it okay if we leave the question answer towards the end, Mi? While people are coming up with the question. Okay, thank you, Mi, for the great talk. So then I would let's move on to the third speaker. Let's see. Mi, would you please unshare the screen? Or
okay.
Maybe Fernando can share the screen.
Okay.
Thank you. All right, let's welcome our third speaker, Fernando Senhora. He's a PhD student at the Georgia Institute of Technology from the USA. He's working in Professor Glaucio Polino's research group. So Fernando, you have the floor.
Thank you, Shelly. Can you guys hear me all right?
Yes.
All right. So I'm Fernando Vasconcelos da Senhora. And before we start, I would like to thank the organizers of the top webinar for this opportunity to share my work. It's an honor to present the same session as so many great researchers. And today I'm going to show our work on optimally tailored Spinodal architected materials for multiscale design and manufacturing that I did in collaboration with Professor Emily Sanders from Georgia Tech and Professor Glaucio Polino from Princeton University. And you can see here in the bottom that I did the top webinar words here using the Spinodal material, and you can see that each color represents a different type of Spinodal material, and the transition between materials is smoothly, and I'm gonna explain this more in my talk. So this work was published on the Advanced Materials Journal, and we are lucky enough to be featured on the front cover in the design that you can see here on the right, where it displays several possible applications of Spinodal architectural materials in civil engineering, mechanics, engineering mechanics, and biomechanics, paving a way to a bright future. And in today's talk, first I'm going to explain what are Spinodal architectural materials and how do we incorporate them into a topology optimization formulation. And then I'm going to show some numerical results and explain how we manufacture these results. So let's start with Spinodal architectural materials. Spinodal architectural materials comes from the solution of the Garner equation that describes the separation of a binary fluid in two phases. And if we interpret one phase as solid and the other void, we can obtain a microstructure. So unlike typical microstructures that are lattice-based, which are periodic and can be highly sensitive to effects, and the properties depend on the design of the lattice, which can be, so it can be hard to obtain the properties that you want. Spinodal microstructures are non-periodic and stochastic in nature, which makes them resistant to defects, and they have properties depending on only a few variables, so it's pretty easy to control, and they have several other interesting properties. So for example, by controlling some parameters of the spinodal material, we can have isotropic material that you can see here in blue, a cubic material in yellow that is strong in triaxial direction, a lamellar material that is similar to a shell-like composite that's strong on a plane, and a columnar material that is similar to a fiber reinforced composite that is strong in one direction. And using homogenization, we can obtain the mechanical properties of this architected material. And we can also vary their density, so we can have a lighter and softer material or heavier and stiffer material. And we can model this, this whole range of densities. Here in the bottom, you can see the elastic surface envelope that represents the mechanical behavior property of this material. And another interesting property of spinodal architected materials is that it's quite easy to make it to transition between two different classes of spinodal materials, densities, and even orientations. You can see here on the left the computational model of several different classes and densities connected together, and you can see here the transition is quite smooth. And on the right, you have actual 3D printed part. And if you guys can look at the camera, I have the actual 3D printed part here in my hand. So this is actual manufactured part, and you can see here in the zoom-ins that the model matches quite well the computational model. And here, when you don't have the transition is so smooth that when you don't have the colors, it can be even hard to tell when a material ends and the other starts. So they have, so architected materials have very interesting properties, and we want to incorporate that into the polymerization formulation. But before I talk about my formulation, I want to give a little bit of historical context. And for that, I want to talk about this paper by Benso and Kikuchi in 1988, generating optimal topologies in structural design using homogenization method. This paper was revolutionary in a lot of ways and shaped the field of structural polymerization. And in this paper, they use homogenization to design using a microstructure that you can see here on the left. And they could control the density of this microstructure by control the size of the hole in the middle. So we can have a lighter and softer material, you can see here. And they can also control orientation, and they did all of this locally. And there were several very interesting and very important ideas in this paper, but one problem was that actually manufacturing this these types of structure that they obtained was quite difficult because of geometrical incompatibilities between orientations of microstructures or even different microstructures, as you can see here. But as I show you, the spinodal architected material can blend quite well different classes, orientations, and densities. So using this material, we were inspired by their idea, their formulation from 1988, and we came up with this from our formulation. Here we have the optimization problem where we minimize compliance with a constraint on the total weight. And we have one set of variables Z that controls the distribution of the spinodal material class, a set of variables alpha, beta, and gamma that controls the orientation, and a variable rho that controls the density of the material. And all of these variables are defined locally. So we can have a local control of the material distribution, orientation, and density, and the ability of the spinodal architected material to smoothly transition between all of these factors allow us to actually obtain results that we can manufacture and use in real applications. You can see here the optimization choosing the distribution of each class of material. Here the black lines represent the orientation of the material at each point, and here on the right you have the spinodal density in this color map. So now I'm going to show some numerical results that we obtained using this formulation. First, the cantilever beam supported here on the left with a downward force on the tip. And although we had 4 candidate spinodal classes that you can see here on the right, the optimizer only chose one class, that's columnar, because of the simplicity of the geometry in the load cases. And here in the middle, you can see the red line represents the orientation of the strongest axis of the columnar material. Remember, this is a fiber-like composite that's strong in one direction, and you can see the orientation aligns quite well with the macro scale geometry. Here, F represents the compliance of this Spinodal result, and F0 represents the compliance of a result using optimized result using solid material. So you can see that this number is below 1, which means that the compliance of our Spinodal architected solution is actually lower than the compliance of the solid optimized counterpart. And here in the bottom, you can see the actual manufactured parts and some zoom-ins. I have manufactured part here. And now just to explain how I actually manufactured this, we use mass stereolithography additive manufacturing. So the way that it works is we have a resin that is sensitive to UV light, and when UV light treats its liquid resin, it solidifies. So we have a build plate here in the top. I'm pouring the liquid resin here. And here in the bottom, we have an LCD screen and a UV light projector. So what happens is we project this image, a slice of image of the microstructure onto the resin, and it gets attached to the build plate, and we raise the build plate a little bit, and we repeat this process. Here in the middle, we have the computational model, and here on the right, we have the slices being projected onto the LCD screen, which slowly build the structure. And another advantage of dealing with slices is that we can quite completely efficiently handle this complex geometry. We don't use SCLs directly, which can be, for these types of detail, can be quite large, a large file, and quite hard to handle in typical additive manufacturing software. So you can see here the time lapse of the actual print being done and being raised from the resin vat as we projected several slices into the LCD screen. So almost done. So here I have another result for the cantilever beam, but now I restricted the spinodal density to a 0.3 density. And you can see it as expected, the result's much bulkier and resembles a shell-like structure. And again, you can see the orientation of the columnar material here is this active axis. And it is quite interesting that it resembles in some sense a shell-like optimal structure. And the last example that I wanted to show is the craniofacial implant that you can see here. Play this video. So this design this was design of craniofacial implant. You can see now the optimization being done. So the optimization shows in the distribution of the different classes of material. And now since the geometry and the load case are more complex, we have the optimizer choosing more than one material, laminar and columnar. You can see it's choosing not only the geometry, but the distribution of different material classes, the orientation and the density. And once we have the solution, we can embed the spinodal microstructure and contain the slices to actually manufacture this part using mass stereolithography. And another advantage of this kind of porous structures for these implants is that they stimulate bone regeneration and integration. So this kind of spinodal microarchitecture can have a lot of different properties that are interesting for many applications. So to conclude, we interpret and bridge the entire topology framework with mass stereolithography and additive manufacturing. We develop a unified spinodal topology framework that accommodates locally varying spinodal class, orientation, and density. And we simultaneously optimize the macro scale geometry and the spinodal material distribution at the micro scale. And I would like to thank again the top webinar organizers, Professor Shelly, Zhang, Princeton University, Georgia Tech University, and NSF for funding this research. And let's now open the floor for questions.
Thank you very much, Fernando. Doing very well on the time. So we have 2 minutes for questions. I think the first question is from Ole. Would you like to ask a question?
Sure, thank you for an interesting talk. I was just curious, spinoidal microstructure is guaranteed to be open-celled, or could you have cases where there's an enclosed cavity?
So that's a great question. So it depends on the spinodal density. And that's why we chose this range of 0.3 to 0.7 density. In this range, we can guarantee that we will not have closed cavities or like disconnected components. If we go below 0.3, we can have disconnected components, and if we go above 0.7, we can have closed cavities that can hold resin during 3D printed, so that's not good.
Thank you.
One more question from Li Wei. Maybe you can ask the first question.
Yeah, sure. Yeah. Hi, Fernando. Thanks a lot for your very great presentation. Yeah, I have one question regarding your manufacturing. I think since the structure is inspired from the Spinodal materials, can we directly manufacture it by the Spinodal decomposition instead of using AN? Because maybe AN will complicate the manufacturing process.
Yeah, that's a really good point, a very interesting question, and it is possible. Spinodal decompositions can be difficult to obtain because they're kind of a special type of phase separation that doesn't have nucleation. And there have been some people that have been able to use kind of like self-assembly materials and to obtain a kind of spinodal microstructure without actually 3D manufacturing. I think was Carlos Botello from MIT. He mentioned that he was working on that and he was able to obtain some quite interesting results. But for now, I understand they are limited to isotropic materials. And that's another thing. Not only it can be hard to control exactly the properties with the spinodal decomposition, but it can be also very hard to change from one type of spinodal class in one point and another type of spinodal class in another point in the material.
Yeah. Okay. Thank you.
Thank you. Thank you, Li Wei. Thank you, Fernando. Very impressive work. Okay, so maybe we'll move on to the next one, and we have plenty of time at the very end for discussions. Okay, so our fourth speaker will be Eric Garner, and he is a PhD student at the Delft University of Technology in Netherlands, and he's working in Professor Jun Wu's research group. Eric, you have the floor.
Hello, and welcome everyone to this presentation. Like Fernando said, it's very overwhelming and an honor to be speaking among this group. Today, I'm going to be presenting some work done by Junwoo done in collaboration between Junwoo and Amir Zadpour's groups at TU Delft. It's about multi-objective design optimization of 3D micro-architected implants. So, as you can tell, this is a fairly application-specific topic, so it's important to go through a bit of background information first. So one, we're going to discuss what are orthopedic implants, what are their current shortcomings, and how can they be improved. So orthopedic implants are simply devices used to replace damaged or missing bone or joint tissue. They're typically made out of very stiff, biologically inert metals such as titanium. And this is one of the main reasons for their very short service life. And this happens because of something called aseptic loosening, and it's caused in particular by two phenomena, one called stress shielding, and the other is interface fracture. So to understand stress shielding, we have to understand that bone is a dynamic tissue. So it's constantly adapting by changing its local density to the current loading conditions. And what happens is when you put a stiff material like an implant into the bone, the surrounding bone tissue is relatively underloaded. And what happens is the bone density decreases, and as a result, you end up with this loosening. So the second issue is interface fracture. So the loading conditions for an implant, let's say a femoral implant, is a typical bending. So what happens is that because the implant is press-fitted and unbonded, the interface stresses cause micro-slipping and interface cleavage. As a result, there's an inflammatory response, which typically starts bone resorption. So interface fracture and bone remodeling exhibit this sort of negative synergy. So both of them need to be handled at the same time. This is the motivation for our optimization. Our goal is to minimize bone remodeling and the risk of interface failure simultaneously. So one way we can do this is by optimizing the implant material. In industry, you find that there's an increased popularity in porous titanium implants, and they're typically a random uniform metal foam. And because they're less stiff than their solid counterparts, there's a reduction in stress shielding, but it's always accompanied by an increase in the risk of interface fracture. An alternative would be to create some sort of non-uniform material properties. As you can see on the right, this was proposed as early as 1990. We can do this by using architected materials. So our goal is to create a multi-scale optimization scheme using heterogeneous architected materials. One approach, as you've heard before, is to use a sort of full hierarchical method where you consider a full microscale design freedom. The problem with this is that it's computationally quite expensive and it becomes difficult to control certain microscale features, particularly connectivity and open cell porosity are difficult to control. So one very, very simple method for handling this is to use a parametric formulation. This can be very efficient because it reduces the number of design variables on the microscale, and it allows us to guarantee certain geometric properties like interconnectivity between cells. However, it limits the design space and the performance is dependent on our parametrization, so it becomes very important to choose our parametrization carefully. So for this reason, we've come up with a generalization of the famous antichiral auxetic microstructure. As you see on the left here, you have the classic antichiral structure where you have a negative Poisson ratio. Now, there's a sort of amplitude, as you see in the waveform. If you were to change this amplitude to, let's say, 0, you can get a sort of neutral microstructure. And if you were to further change it by flipping one of the two, in this case in 2D, or one of the 3 in 3D waves, you end up with a sort of hyper-positive Poisson ratio. So a Poisson ratio greater than that of the base material. Now, if we add a second parameter, let's say the diameter of the waveforms, you can change the stiffness as well. One benefit of this structure is that it's open cell and you can get very good connectivity guaranteed between the individual unit cells. So from there, we can sample the design space and we can interpolate between the properties to create a relation, or to obtain the relations between the geometric properties and derived mechanical properties or other geometric properties such as mean density. Then we can use these values or these relations directly in our optimization so that we don't need to perform any homogenization during the optimization scheme. It also allows us to apply constraints directly on the design space. For example, you see the design space on the left here, the original one. You could add some constraints, for example, maximum density or further minimum length scale. And what you obtain is this bitmap. And you can take this bitmap, create a distance field, and then create a cost function that is simply the sum of the distance field for every one of the design variables. And this, as we'll see later, works very effectively. It also means that there's 0 additional cost to each new constraint, since they're all added to the main constraint. So let's revisit our design objectives. We use, in order to quantify bone remodeling, we use a modified version of the famous Hauskes model. The Hauskes model basically defines 3 different scenarios. Between two thresholds for strain energy density, you have stable bone remodeling, meaning no net loss or gain exists. If you fall below this threshold, there's some net bone loss, and if you go above it, there's some net bone apposition. The problem with this model is that it doesn't consider the current density and is not differentiable. So we propose a modified version, as you see below, which is differentiable and therefore can be used in our optimization scheme. Then we define our bone remodeling objective as simply the sum of the unsigned changes in bone density throughout the bone. For the interface fracture risk, we can use a simple multi-axial Hoffman criterion, which evaluates the local risk of interface failure as a function of the normal and shear stresses present. Then we can use a KS function to find the soft maximum over the entire interface. So now we have everything we need to formulate the optimization problem. I just note that we consider multiple load cases, in this case L, and we consider a worst case formulation. We use linear scalarization of the objective, so we just take weighted average of the two, or in this case a weighted sum, sorry. And then we, in order to make sure that one objective is not favored too much over the other, we add constraints to each one of the objectives. In this case, we're quite ambitious and we constrain the bone remodeling objective to be better or equal to that of the porous uniform implant, and we constrain the interface stress constraint to be better or equal to that of the solid counterpart. So now I'll show you some results. On the left here, you see a solid titanium implant. On the very left of the figure, you see the bone remodeling, which is in red, and then on the right, you see the interface stresses. So in this case, as you'd expect, bone remodeling is very significant, but the interface stresses are relatively low. When we look at a uniform lattice, As you'd expect again, we get much lower bone remodeling, but the interface stresses are very high. So when we look at the optimized implant, we actually see that we get sort of the best of both worlds. In fact, we actually outperform the uniform lattice in terms of bone remodeling, and we slightly outperform the solid titanium implant in terms of interface stress. So if we want to look at the property distributions, on the top row, you see the design parameters, so the amplitude and the diameter, and you see a very non-uniform distribution. You see on the right, the distribution in terms of the design space, and it spreads throughout the design space, but for some reason, in this case, it seems to have favored positive amplitude values. On the bottom row, you see the mechanical properties, which again are quite non-uniform. Now, if we look at the if we look at constrained design, where we say for manufacturability reasons, we want to constrain the amplitude and diameter according to the figure here, we see that we get a very different property distribution. But when we compare performance, we actually get, I'm sorry, I need to move this bar. Yes, we actually get fairly good performance compared to the original unconstrained optimized structure. And we still outperform the solid and the solid implant in terms of bone remodeling and nearly match it in terms of interface stresses. So even with this constrained scenario, we still do very well. Looking a little bit at the optimization history, we see here from the black line that we get monotonically decreasing objective. It's very smooth, but we eventually do get some conflict between the two objectives because of the stress constraint, which is shown here in pink and is originally very much violated. So in order to bring this into, to handle this, the optimization algorithm eventually favors the stress objective over the bone remodeling objective, which is shown in blue and starts to increase after a few iterations. So in conclusion, we've presented an efficient parametric multi-scale strategy which uses, in this case, the generalized anti-chiral microstructure, but can be used for any different microstructural class that we decide. We also shown zero cost inclusion of microscale design constraints, and we've shown that it can be used to improve the performance of a typical hip implant by 15% in terms of interface stresses and as much as 45% in terms of bone remodeling compared to a solid implant. There are a few questions we'd still like to look into. The first is, how much is performance sacrificed by using our parametric formulation as opposed to a more open, free design space? Another thing that's really important is how can we consider microscale stresses and how can we constrain them? Because in our case, we rely on this decoupled method. And so we don't have any way of accurately capturing and constraining these local behaviors. Another question that's very much relevant for the application is there a one-size-fits-all design, or is this patient-specific approach really the best way to go? Another question I'd like to look into is, how much does the shape of the implant matter? And can we simultaneously optimize both the shape and the internal structure? Thank you very much for your attention, and I look forward to your questions.
Thank you very much, Eric. Very impressive work. We have some time for questions. So I will first look at the first one would be Ole. Would you like to ask a question?
I think I will hand it to Julian. I already asked a lot, so maybe Eric can answer on the chat.
Yeah,
sure.
Julian, would you like to?
Yes, sure. Very nice presentation, Eric. Thank you very much. So if I understand correctly, you're trying to stay in the lazy zone to avoid receding bone and also bone apposition, right? So does that mean there is no osseointegration with the porous implant?
I'm sorry, I didn't quite follow. I don't model a bone integration. I simply ensure that there is porosity so that bone integration can occur. Is that the question?
So when you look at the Huysken's model, right, you have that lazy zone where essentially there is no bone growth or bone loss.
Yeah.
And you're trying to stay within that region, right?
Yeah.
So does that mean if you're successful when you do the optimization in staying within that zone, does that mean that there is no integration of the bone with the porous implant on the surface?
So actually, I don't actually constrain the design equally on both sides, meaning that I prefer for there to be ossification than bone resorption. And so you can tune the different parameters to allow for, let's say, as much osseointegration as you'd like, or even to force it to go in that direction. Another thing is that typically you would coat these implants with hormones so that bone integration or bone growth happens naturally even without these stresses.
Okay, thank you.
Yeah.
Thank you. Next we have Ajit. Would you like to ask a question yourself?
Yeah, thanks, Eric, for the lovely talk. I was just wondering, perhaps you have already covered this briefly. Do you incorporate stress shielding by any chance? And
Yeah.
how would you go about that?
So stress shielding and bone remodeling are very much related, right? So stress shielding causes this bone remodeling, and the bone remodeling is really the thing we want to avoid. So that's what that's one of the two objectives of the optimization, is to minimize the bone remodeling. Stress shielding is more of a vague term that you can't really quantify the same way you can quantify the bone remodeling.
Perfect, thanks.
Thank you, Ajit. All right, we are right on time. Thank you, Eric, for the great talk.
Thank you.
Yeah, okay, and please keep typing the questions to the chat and we can leave them to the end for extended discussion. So, all right, last but not the least, let's welcome our last speaker, Professor Ole Sigmund, who is a professor from Department of Civil and Mechanical Engineering at Technical University of Denmark. So, Ole, you have the floor.
Yeah, thank you very much. Can you see my screen?
Yes.
Okay, perfect. So thanks a lot for the invitation to give this talk. In reality, I am speaking on behalf of 3 excellent young PhD students where I'm putting together 3 different papers in one talk here. And so actually these 3 students, Rebecca, Christopher, and Peter, could individually give a talk in this, and maybe this is an invitation to future top webinar organizers. But anyway, let me start by motivating multiscale topology optimization. And so, for example, nature uses multiscales a lot, as seen, for example, in the bone microstructure or in tree structures, bamboo. And there are some incentives partly to get stiff and strong structures, but also to have some permeability and therefore have open cell structures. Now in additive manufacturing, we see a lot of beautiful structures, but sometimes the reason for multiscale, like in the lower right corner here, is not clear. And certainly the stiffness is highly suboptimal when used in this way that we see here. So it's not always clear why people are using multiscale and microstructures. But so why should we use it? Well, partly we want to do topology optimization of multiscale structures to save resources and make more efficient optimization. But we also want to look specifically at gains for multiscale. And I've put question marks to stiffness, strength, stability, and redundancy, because it's something that's often claimed, but not always proven that a multiscale provides improved properties like that. But certainly, if you require permeability or manufacturability, you may ask for open wall structures and also for metamaterials. So I don't have time to talk about all this today, but I will mostly concentrate on stiffness and stability aspects of multiscale structures. And regarding stiffness, I just want to emphasize, and it's something I've been speaking about before, that there has to be very special reasons to use microstructures, because actually often the solid structure or anisotropic structures are much better than isotropic structures. And so, for example, what we often see is an isotropic truss lattice structure, but if we look at its relative modulus versus volume fraction, well, then it's a very low stiffness you get for open wall truss structures. And therefore, they are not really optimal for any kind of stiffness optimization. Even if you go to isotropic plate-like lattice structures that almost realize the Hessian-Strickman bounds, you still see that the stiffness is quite low compared to an anisotropic adaptive microstructure that has the linear response. And then finally, if you have an orthotropic structure that's oriented along the principal stress directions, you may do better, but still they are not really favored because you get less than proportional stiffness for a certain volume here. So when we consider pure stiffness optimization, isotropic microstructures, whether open or closed, are actually not applicable or not relevant. You want to do an isotropic design. So where can you use isotropic microstructures? Well, in a work some years ago, we postulated that we could improve buckling behavior. So for example, we looked at infill optimized MBB beams we looked at different infill densities, and we showed that at a small increase in compliance, we could actually get a huge increase in buckling performance. And so this is where we could possibly use isotropic microstructure. A caveat to that is actually that at some point when the volume fraction of the local infill goes down, then we will have local buckling of the microstructure, and hence there's limits to how much we can gain in the global buckling load. And so in fact, we did experiments and found that the local buckling behavior was what determined the global response of the structure. And hence in that paper, we postulated that isotropic infill structures are inferior in stiffness, but may be superior for stability, as long as we ensure that microstructural stability is ensured. And actually nobody ever proved that systematically, we just postulated it in that paper. So I will get back to that. So we want microstructure, we want multiscale if we use anisotropic material structures for stiffness, or we can use it to get better buckling resistance. So we need multiscale topology optimization. And the way we are doing it is actually going back to the original work by Bencio and Kikuchi. It was earlier today mentioned that it was difficult to realize these structures. And truly, this is also probably the reason why this homogenization approach that used knowledge of optimal microstructures oriented in the orthotropic directions of the stresses, why they weren't continued for many years. But actually, there is a lot of information in here. So at every point in such a homogenized solution, we know the optimal material orientation and the lamination parameters in the two directions. So it's only a matter of extracting these structures out of this, the so-called de-homogenization that we have been pursuing for several years. And so the idea is that we start by doing a core scale homogenization-based topology optimization that finds the optimal orientation and lamination parameters. Based on that, we introduce some auxiliary fields, the special condition that their gradients correspond to the local lamination directions in the homogenized solution, and also that the slope is always as close to unity as possible. If we locate such fields by a least squares problem, then afterwards we can take the cosine of these fields, we can reintroduce the lamination thicknesses, and we can approach fine scale solutions like this one at a cost that is hundreds or even thousands more efficient than doing a fine scale topology optimization from the beginning. So this we have done together with Jerome Brun and others for a while, and we have produced all these beautiful structures, the de-homogenization that approach the theoretical stiffness optimum. We have done it in 2 dimensions, and we have done it in 3 dimensions, as we see here also. Now, up to now, everybody has been looking at simple load case problems, meaning that the microstructure is always oriented along the principal stress directions, with 3 directions in 3D and just 2 directions in 2D. Now, if we want to go to 3D, and this is some work by Peter Jensen, our PhD student, and Jerome Brun, if we want to consider a multi-load case, in this case just 2 load cases, well, then it turns out that the optimal microstructure requires at most 3 lamination directions, but it also complicates the problem now because we have 3 individual angles and we have 3 thickness values. So the homogenization problem becomes somewhat more complicated. Just as a reference, I will show you a standard SIMP obtained solution here for multiple loading cases. And this is run with very high resolution, more than 2 million elements. And due to various continuation approaches, this took 18 hours and had a certain compliance of 1.6. Now, if we do the homogenization-based topology optimization, we would get a design looking like this. And if we enlarge the region here, we will see that at any point there are at most 3 directions. And then if we perform the de-homogenization of that, we get a quite beautiful structure looking like this. And what we see, the first thing is it's just slightly worse than the SIMP solution. But the really nice thing is that it only took 5 minutes, whereas it took 18 hours for the same resolution with the SIMP approach. So this is a factor of 200 or something like that. Now you could ask, hey, this looks like an isotropic microstructure, right? So couldn't we just use an isotropic instead of having these 3 independent angles? So we actually tried to optimize it using optimal triangular isotropic microstructures. This was extremely efficient. We did the de-homogenization, but what we see here is that the compliance is significantly worse. So we still need anisotropic adaptation when we do stiffness design. So this was a stiffness case. We also have various other cases. I should say that there's quite a dependency on the starting guess. So it's not fully resolved, this problem, but if you want to know more, you can look up this paper by Peter and the rest of us. So this was stiffness optimization. Now let's get to the buckling optimization problem. And this is work by Christopher Christensen. So we started by looking at the simple compressed cantilever problem or compressed column problem. And we first, as a reference, optimized this using the standard SIMP approach, and we get this reinforced column structure that has a certain eigenvalue 8.36. Now, if we introduce multiscale in the shape of an isotropic microstructure, well, then we get a structure like this. And interestingly now, there is a demand, or there is a need now for microstructure. And with this microstructure, we are actually able to get a higher buckling value. So this is very nice. This looks interesting. We actually need isotropic microstructure. But if we de-homogenize this structure and actually realize this structure with a very fine grid here and do the trusses here, we will see actually that we have local buckling before we have the global homogenized buckling. So this structure is really no good because we didn't consider the local buckling. So how to consider local buckling? Well, we need to provide yield surfaces or buckling yield strength surfaces. We do that by doing an intensive number of floated block wave analysis. So we assume an infinite periodic structure. We perform the so-called floated block wave analysis and find the most critical modes. And then for this specific structure, this would be this point here where we have those critical buckling modes. And so we do that for several different stress situations. And based on that, we are able to provide yield surfaces. So the black dots here are provided by the floated block wave analysis. Then we locate a suitable yield function. And in this case, it actually turns out that the Willem-Wonke yield surface approximates our microstructure buckling response quite well. And so to do the topology optimization, we use an approach that was advocated by Geraldo Rondonio and Paulino to do this. So what comes out of this? Well, let's have a look. So the test case we are looking at is a sort of rotated L-beam structure here. First, as a reference, we do the compliance design. We just get a vertical column here that obviously has a very low buckling load. If we do buckling optimization still with the SIMP approach, we have a slightly higher compliance and a much higher buckling load. But now if we introduce isotropic microstructure with variable density and the local and global buckling constraint, then we see again that we slightly increase the compliance again, but again, we get a much, much higher buckling load here. So this is, I believe, the first case of considering simultaneously local and global buckling load. So now the question is, does it work in practice? And so we de-homogenize these solutions, and obviously you can do that with different periodicity. And so by having smaller or larger cell sizes, you can actually test the validity of the separation of scales that was used in the original homogenization part. And well, what comes out of it is actually surprisingly nice because it performs better than the homogenization solution. So for small cells, we get a buckling load of 3, which is higher than the homogenization solution. And for larger cells, it still works surprisingly well. Sometimes we get the global and sometimes the local buckling modes, as we see here, but overall it works really nicely. And if you want to know more details about this, this paper was just published on arXiv yesterday. So now, towards the end of my talk here, I have 2 minutes, I guess, still. Then let me just talk about the elephant in the room, because here we have shown by systematic topology optimization and de-homogenization that we can do very well. But the question is, could we do just as well using artificial neural networks, both in multiscale topology optimization or in conventional topology optimization? If you read the literature, you see a lot of promise out there and a lot of bragging about things. Our very good PhD student Rebecca did an intensive survey, which was just published in SMO, about the state of the art in AI for TO. And we must say that the outcome is somewhat disappointing. So Rebecca categorized various categories of applications of artificial neural networks in topology optimization. Everybody's wet dream seems to be directly substituting topology optimization by a trained neural network. We did not see much promise there, and it essentially be discouraged doing more in that because it doesn't seem like it's the right way to go. However, there might be other ways where we sort of taking subparts of the topology optimization and improving it through acceleration, reduction, post-processing, or design diversity. Obviously, I don't have time to go into all this. I just want to focus on one application, which was de-homogenization. So if some of you heard my talk at last year's WCSMO, I was quite fond of using ANNs for de-homogenization. And so let me just shortly remind you of that. So our idea back then was to replace the de-homogenization process by a trained neural network. And instead of training it on very expensive topology optimized data, we trained it on random orientation fields. And so this was very cheap. Then we could do the de-homogenization, and after some post-processing, we got actually quite good-looking structures, and we were pretty proud to present de-homogenized solutions like this one. Now, there was still some issues in that, partly with these forks here that had rounded forks. So again, our PhD student, Rebecca, looked into this and tried to improve on this. And in fact, she found that we can do better, or we can do the same or even better without deep learning. And so this is not published yet. I just want to flash two pictures. So this was the old results obtained by convolutional neural networks in the paper published this year. We got designs looking like this. With Rebecca's approach that is simply using traditional computer graphics, she is actually able to produce better de-homogenized solutions. So to be a little bit provocative, we must conclude that we have so far not really seen convincing uses of artificial intelligence in topology optimization. But who knows, this may be coming, and the review paper certainly has some ideas for that. So this brings me to the conclusions. Just 2 points I will emphasize here. Partly, I believe we need to consider the stability of the infill when we do topology optimization for multiscale structures. And I would say that efficiency of artificial neural networks in inverse design problems has yet to be proven. And we urge both authors and readers to be critical when you look at the claimed results in this field. And so with these statements, I will just list the various papers that were relevant for this talk, specifically the red ones that were produced by Peter and by Christopher and by Rebecca, but obviously also the other ones that are relevant for this talk. So thank you very much for your attention, and I hope I wasn't too fast, but you could grasp some of what I said.
Thank you, Ole. Great presentation, very informative. We have a quick one question from the audience. So Jun, would you like to ask a question?
Yes, sure. Ole, about this ANN for de-homogenization. So if the field is very smooth, I can understand it would work pretty well. But if in an optimized field, if we have some singularities, and do you train the ANN with a lot of singularities in order to get good results, or how does it work?
That's a very good question, Jun. So this is still one of the weak points in the whole field of de-homogenization to treat the singularities. But in the paper with Stutz, this fifth paper here, we did discuss, there was also another one, sorry, but we do discuss these issues. So if you have a cone field or you have a clean field, then it works quite well. We are still looking into improving this with the singularities, or also if the order of the directions is not well ordered. So this is still a challenge that we have to admit. But yeah.
Thank you.
Thank you, Jun. Thank you, Ole. Wei, would you like to ask your question?
Yeah, So first, really enjoying all this talk. I managed to come back from another webinar to listen to you. And I kind of agree with you that the deep learning and those methods doesn't prove to be effective in we call the design synthesis, right? The inverse problem. But on the other hand, a neural network has been useful to surrogate analysis model, right? Like find an element that I think it's in one of your slides. So I agree with that statement you made. And I feel like in our research, we also went through a process and we realized, the data-driven methods probably would be more useful for multi-scale kind of problem like we presented today. But there's still some challenges. So I'd like to hear your thoughts on this de-homogenization for nonlinear problem, like generally, we have some thinking about in our work, how we extend to nonlinear problem. But I'd like to hear your thoughts on nonlinear problem that may involve soft material systems.
Yes, thank you, Wei. And definitely some of what you have been doing is not in the category of direct design, but rather in the other categories where we do see promise for this. Regarding the nonlinear problems, essentially, if you are able to come up with microstructures, so in principle, you can have these multiple directions, and you can optimize that for a geometrically nonlinear model, just as we can do it for buckling. And then the de-homogenization should work fine. So it doesn't really depend on the nonlinear or the linearity of the problem. But you may, of course, ask whether it's actually necessary. So for soft robotics, do you actually need to optimize the stiffness for those? And would it then, or are you optimizing for other properties like negative Poisson's ratio or whatever? So it would depend on the problem, but really de-homogenization, we do it for these simple laminates that follow directions, but the original work on these methods, they can also project Mickey Mouses or other things, so it doesn't really require simple microstructures.
Thank you, Ole. Okay, so now I think we have the floor for the open discussions. I do have one question for Ole, just posted there. So I was wondering, in addition to, for example, buckling, could you please also comment on, for example, if we would like to consider the strength in the de-homogenization, essentially in addition to the homogenized stiffness, would it be possible to also consider homogenized, say, yield surface?
Yes, it's such an obvious question. In fact, if Christopher wasn't listening to this talk, which I hope he is right now, then he would be working on this. So this is our next spot. So in principle, we have the yield surfaces for the buckling part, and now on top of that, we would also put the yield surface. We would have the strength surface for the buckling, and on top of that, we would put the yield surface, and in that way, combine both of them. So this is exactly what we are doing now.
Sounds great. Thank you, Ole. All right. So maybe we could open the. Oh, wait, please.
Don't mind if I want to add a comment to the comment I made earlier about this deep learning for inverse design. I don't want to make people misinterpret the statement. I would think that there are still cases that if you do deep learning in an intelligent way, that there could be still cases that could be useful. For example, I'm just thinking about because traditional TO method, you always have this starting solution issue, right? It's kind of sensitive. So if you say you consider different classes of concept to begin with, right? And you kind of do machine learning from this different creative idea, and then they help you to kind of converge to maybe stay outside of the trap of the local solution. I think there's still some room for using deep learning, but you have to do it in a way that is that really makes sense, that value adding, to put it that way, and thinking about the whole design process, not just treat it as a black box computational exercise. So I just want to comment.
Thanks, Wei. I completely agree. And if you read the paper, we are also very constructive in some of these subtasks. So we are quite critical towards the direct design phase, but the other ones we see a lot of potential. Whether to use it for generating starting guesses, I don't know, because it's also very expensive to train your network. So there has been in the photonics community, they do it a lot. And really, I don't see the big promise in they do train a network with 500 optimized designs to provide starting guesses. So why couldn't we just start with 3 different starting guesses as we usually do? So my main thing is it's not that I'm not sort of on a fight against AI, but I'm on a fight on people using it should be honest and compare it to existing state of the art and not make too many claims of where it's better without actually comparing it to the state of the art. So this is where I see the main problem here.
Great. Thank you for the discussions. So I think, is there any questions that are coming up from the audience for any of the speakers? I think one of the things that I saw that could probably be addressed in the audience is, I think it was the second question from Li Wei for Fernando. For example, how's the optimality of a spinodal structure compared with a lattice-based structure in terms of compliance performance? Will this be, or maybe you already answered that?
No, sorry, I think I might have missed.
No worries. Yeah.
So one of my collaborators, Professor Emily Sanders, worked with lattice before, and in her work, what she found was very difficult to obtain compliance that were comparable with the stiffest, like with the solid solution using lattice-based architectural materials, because not only like it's very hard to orient them, you cannot freely orient them, and their properties are can be limited, and you cannot vary as much density without compatibility problems. Since with the Spinodal material we have a lot of liberty, we were able to actually obtain performance better than the solid counterpart. Of course, this depends a lot on the problem that you're solving and also the optimization metaparameters of volume constraint and filter radius all play a part. And there are a lot of applications that I think multi-physical applications that Spinodal materials could be interesting. So yeah, well, like we have a lot of research to do still. I hope this answered quite a good question.
Yeah, thank you, Fernando. And finally, I just want to ask a quick question, maybe to the all the invited speakers. So one thing we see that I observed today is that we have quite a various different approaches in the literature, considering different type of unit cells. Would you think it would be useful or have some suggestions on some benchmark examples for the research in this area to compare and verify their approach?
Yeah, I can give a quick response to this, is that design problem is not one-to-one mapping. So it's one-to-many mapping. So for like using our top-down approach, we realize that for the same property, you can have many different kind of structure to accomplish the same goal, right? So at the end, I think is a balance of manufacturability and the performance. So manufacturability has to be taken into account. So some of our bottom approach is really try to stick to some of the class that we think is more manufacturable. And Ole also mentioned some of the isotropic structure are more like anti-buckling. So I think those knowledge need to come into ahead of time to determine what kind of class we want to go with, or multiple class. So I think it's more a manufacturing issue rather than the design issue. From the design point of view, the design freedom is huge. You can do anything you want with the lattice structure.
Thank you, Wei. Ole,
can I comment also? So I think I showed it here that we compare to the Hessian-Strickman interpolation there. So I think this is like a good benchmark. If you use, instead of SIMP, you use a Hessian-Strickman interpolation, that should give you a benchmark for what can be achieved by an isotropic structure. And then you can compare your approach with that and then evaluate, is it acceptable that we go up 50% in compliance if we introduce this and that manufacturing constraint? So I think the Hessian-Strickman bound is actually a good sort of performance measure for other methods, and sort of to weigh how much importance you should put on the manufacturing part.
Thank you, Ole. All right, so I think just a final remark. I think also it's great to see that many of the talks and also the ongoing work involve the physical demonstration of the multi-scale structure. So because the validation seems to be very particularly important, especially for this very complex design that involves different unit cells.